So if you were to analyze an antenna, there are two different ways we can analyze it. One is in the circuit approach and another one is the radiation approach. So from a circuit approach, the fundamental idea that makes the analysis of antenna easier is that the entire antenna can be represented by an load impedance called as the antenna. So whatever all this while that we have been talking about as the load impedance, that is terminating a certain characteristic impedance Z naught, is all applicable now. It is just that the antenna is replaced as if it is a certain load Z antenna. So in that sense, you have this antenna impedance to be having a real part and an imaginary part. It has a resistance and a reactance. The input impedance is what we can characterize this antenna as. So the reflection coefficient that we defined earlier as ZL minus Z naught over ZL plus Z naught is still the same. The reflection coefficient at the load end becomes the reflection coefficient at the antenna end. It's exactly the same. Instead of ZL, I'm having Z antenna. So the advantage of this expression is that if I know the antenna impedance, I can find the reflection coefficient. And for your lab 2, you would have done the other way around, meaning you would have measured the S11 or the reflection coefficient, and then you would have figured out the antenna impedance. So then this becomes the subject. Then you can go ahead and make this as a subject and rearrange these terms. You would end up getting this expression here, where it is Z naught 1 plus gamma A over 1 minus gamma. Exactly what we have even in the case of transmission line terminated by a certain load ZL. So having this reflection coefficient, we can define what is the return loss. Higher the return loss means there's a perfect match, meaning all the power is getting accepted. What is getting in return is very low. So exactly what we defined as return loss earlier, which we defined as 10 log 10 of, which is the same as S11 square, S11 being the reflection coefficient for a single port device. It's all the same expression. So since how we defined for VSWR before that we could also read from the Smith chart earlier, we can have the same standing wave ratio defined for the antenna as well. Just that in this case, the antenna is the load. ZL becomes the antenna impedance. So when there is a match condition, when the antenna is matched, the reflection is very close to 0. In terms of dB, it's negative infinity dB. That means negative very low value. The S11 is very low. The reflection loss is infinite. Reflection loss is the negative of S11 in dB. So this is negative of S11 in dB. Yeah. And then you have VSWR, which is equal to 1, means it's a perfect match. If there's a mismatch, VSWR will be a big number. So then we can go ahead and define what is called as the impedance bandwidth. The minus 10 dB bandwidth is to define at what frequencies am I having a reflection loss which is less than minus 10 dB, at what different bandwidth of frequencies. So to figure that out, you can view the antenna impedance either in terms of frequency versus the R, which is a function of omega, as well as X, which is a function of omega. So the resistance changes with frequency, so does the reactance, it changes with frequency. So the frequency when the reactance is 0, that's when you call it as the resonant frequency. That is the antenna's operating frequency. Typically, it is the resonant frequency of the antenna. When the reactance curve, the red curve becomes 0. When the red curve becomes 0. And your resistance is a positive number. So that frequency is the resonant frequency. So the same impedance can be viewed in terms of gamma, or the gamma antenna, the reflection coefficient. And then we can define the 10 dB bandwidth to be the crossing line where the return loss is higher than 10 dB. That means S11 is lower than negative 10 dB. The two frequency points, the higher frequency and lower frequency, that's noted. This is the higher and this is the lower. The width between them is the bandwidth. That's the bandwidth of the antenna where the antenna can be used. That's the operating range of frequencies where the antenna can be used. So we know that the reflection coefficient, this guy is the magnitude of the reflection coefficient. If you were to plot it in the complex form, we can get the Smith chart. Yeah, we not only get the magnitude but also the phase. So the real part of the antenna is Z antenna. If I divide it by Z0, then I'm normalizing it. And then the real part, if it's below 0.5 and if it's above 0.5 and below 2.0, then we say that if it is inside the circle, which is the gamma is equal to minus 10 dB. That's the minus 10 dB circle, which means all these points that you see where the gamma is less than minus 10 dB are going to be these frequency points, the response that you see here. Whatever that is outside the minus 10 dB point are this guy here, and this guy is over here. Notice that in the Smith chart, the farther the point is from the center, the greater the mismatch. So the closer the point is to the center, the match is very good. And if the match is very good, then the reflection coefficient is less than 10 dB. 10 dB means 10% of the power is reflected back. Means 10% of the incident power is reflected back. So you can view either an impedance or reflection coefficient or Smith chart. Yeah, to identify the resonant frequency when the antenna. This point is going to be the resonant frequency when there is no reactance. It's on the real line, and that line is very close to the match condition. So the deeper this gets, the more closer it gets to the center point.